Hello everyone, this is Elisa Baum, Percona's Director of Product Marketing. We will begin in just a moment, but first I'd like to conduct some house cleaning. Would you please raise your hand in the GoToWebinar control panel to let me know if you can hear me? Can everybody raise their hand if they can hear me? Okay, great, thank you. I see hands. Okay, next, during this webinar, you will be on mute. Should you have any questions during the discussion, please enter them in the questions field within the GoToWebinar control panel. At the end of the webinar, we will take as much time to answer as many questions as possible, and those that we don't address will be answered in a follow-up blog post on our MySQL performance blog. In addition, a recording is going to be made of this webinar, and the slides will also be available to everybody within 48 hours after we're done today. So with that said, I'd like to thank you for attending today's webinar, Implementing MySQL and Hadoop for Big Data, presented by Percona Principal Consultant Alexander Rubin. With that said, I'd like to turn the floor over to Alex. You have the floor.
Hello, everyone. My name is Alexander Rubin. I'm a principal consultant at Percona. I've been working with MySQL for over 2 years. Started at MySQL AB. I work at Sun Microsystems, then Oracle, doing MySQL consulting. I also worked at Hortonworks at some point, and I joined Percona in 2003. So this webinar will be about big data, and specifically about Hadoop and MySQL and the ways to implement big data with those two solutions. So our agenda for today will be to talk about typical Hadoop use cases, and then I will show you the Hadoop and how Hadoop is designed. We will talk about the big data in general and big data with Hadoop. We'll talk about MySQL and Hadoop integration, the way how we integrate those two solutions. And finally, I will show you the Sstart Schema benchmark that I have recently done. Now this webinar is also quite similar to the talk that I did recently at MySQL Connect. I have included some new slides. Now let's start with this. When Hadoop makes sense, and when do we want to use Hadoop instead of MySQL? So the answer is big data. When you have a really big data that doesn't fit into the MySQL normally, then it makes sense to implement a special solution for big data, for example, Hadoop. So there's a good definition of the big data called 3 V's of big data. And those V's are, first of all, of course, volume. With a big data field, we are talking usually about petabytes of data. Even hundreds of terabytes of data can be considered big data as well, but usually petabytes is definitely a big data. The second V is variety. It can be any type of data, and usually with the big data solutions, we are talking about unstructured or raw data. We also talk about, we don't have any normalization in this case. So unlike MySQL, where we have structured data and normalized data, and in MySQL we usually define our fields ahead of time. We define varchars, we define integers, and so on. With the big data solutions like Hadoop, we work with the raw files, the text files. And finally, velocity. Our data is collected at a very high rate and loaded into our big data solution. Now let me talk first about the typical Hadoop use cases. Clickstream is one of the first Hadoop use cases that was implemented by Yahoo. And Clickstream is a data trail for a user visiting a website. And in this use case, we will store and analyze the clickstream data in Hadoop. And based on our analysis, we can make a decision how to improve the user experience, how to improve our website, how to make it better for our visitors. Another typical example for Hadoop is risk modeling and fraud prevention. For example, banks and financial institutions can store all customer activity and run analysis on top of that to identify the credit card fraud. That's another typical example of the Hadoop, because there may be lots of data, and this is unstructured data, and data are coming at a very high rate. Another example is a point of sale analysis, or so-called also bot algorithm. So if we're talking about the grocery store, grocery stores are usually also interested in which products are sold together. So they can analyze this data and organize the shelves so that they will increase the sales. That is also a typical Hadoop use case. And finally, the stock and historical price analysis. This is also a task that can be solved effectively with a Hadoop. Lots of, for example, hedge fund can analyze the historical prices and make and develop the algorithms for better trading, high-frequency trading. There are much more different other Hadoop use cases as well, of course. Now let's take a look inside our big elephant, and we will see how the Hadoop is designed. Let's start with the data. Usually a database administrator or data analyst or system administrator will start with this question: where is my data? And in Hadoop, the data are distributed and spread between many machines. They call it data nodes. And this is designed as HDFS, Hadoop Distributed File System. Now, the Hadoop Distributed File System, or HDFS, is on the bottom of the system. And HDFS is designed to store the files. And we can write the files, and we can also append to a file, but usually we are not able to update the file. We can delete or drop the whole file and rewrite it again, but we cannot update or delete an arbitrary string inside of the file, unlike in MySQL where we can do updates and deletes. So Hadoop doesn't support that. It's write files, append only mode. And then on top of that, we can use a MapReduce framework to read and process the data. MapReduce is a part of the Hadoop environment. And inside of the MapReduce, the code is executed on the data node inside of the HDFS. So a typical MapReduce task is basically a jar file which is copied over to all the data nodes inside Hadoop, HDFS data nodes, and the code is executed there. So that gives us a very important feature of Hadoop, parallelism. So unlike MySQL and normal MySQL, where the data is stored on one physical system, and when you run a query, you will execute it on top of the MySQL. And the only thing that you can do with the MySQL instance, if you don't implement some sharding approach, is scale up. Hadoop has the scale out of the box, and this is based on the MapReduce. Now, on top of that, we have usually Pig and Hive. Pig is a scripting language, and it translates the script into MapReduce job. Hive is an SQL level for Hadoop, and it executes SQL and translates it into MapReduce job as well. So many people think of MapReduce as an assembler language for Hadoop, and Pig and Hive as a scripting language on top of the Hadoop. And then also usually on this picture is HBase. HBase is a key value NoSQL store. We will not talk much about that in this presentation. Now let's talk about Hive, because this is SQL solution and probably most of you are familiar with the SQL level. So it provides the SQL level for Hadoop, and what it did is usually translate your SQL into a MapReduce job that will run on top of the Hadoop cluster. And also what it happens here is that the result of the MapReduce job will be usually a number of files. So when we run a select, we will expect the results to be loaded somewhere. Or we can also output it into the screen. Now, the important feature of the Hive and how Hive is different from MySQL is called Schema on read. So Hive doesn't check the validity of the data on load. Instead, it usually expects that we have a text file as a table, and when we select from this text file, it will check our data. So here's the example, and it's called Schema on read. Here's the example. We create a table line item, and we also declare our fields like order key is integer, and L discount is double, and the line status L ship date is string here. And then we specify the row format delimited, fields terminated by whatever we choose as a delimiter. This is similar to MySQL's load data in file. So when we created this table, it will create a blank file on top of the HDFS. The next thing we will need to do is to load data into this table. And that will not process the data. It will simply copy the file over into the HDFS or copy it over from HDFS to HDFS. Now, when we select from this table, then this row format delimited and fields terminated by will be executed. So it will split our text file into the chunks, so it will be able to basically execute our select. Now, another example here is that we can create an external table. Let's say we have already loaded our text files into SSB line order, and that will be our table. In HDFS, all the files can be easily concatenated, so we can actually declare a directory on top of the HDFS. And again, this is SSB line order is a directory inside of the HDFS, not inside your local box or not inside some Hive node. And then when we create an external table, it will expect this to be a file with a delimited format. And then again, when we select from this table, it will process our schema and select the fields and execute the where condition. So that's called schema on read. And here's how we can create tables in Hive. Now, one of the problems with the Hive is that it will translate our data, translate our query into MapReduce job. And this is usually slow because it will have to generate a jar file and we'll have to copy it over to the data node. Now, we have another project called Cloudera Impala, and this is not based on the MapReduce. It directly gets the data from HDFS. So the way it works is that Cloudera supports the Impala daemons that are running on each data node. And our Impala client or a shell or your application will connect to this daemons and select the data directly on top of the HDFS. And that's usually faster. Now let's talk about the differences, Hadoop vs MySQL for the big data solution. First of all, let's talk about this. The major way of improving the performance for MySQL is obviously indexes. We add an index and we expect the index scan will be much faster than a full table scan. The second possibility in MySQL is partitioning. We have a really large table. We can partition it into multiple chunks, and then if we have a select query that only reads from one chunk, the table scan for the partitioning will be faster. And then finally, with the sharding approach, our MySQL cannot actually be able to handle our load, or will not be able to handle the amount of data it needs to store. So instead of using single MySQL instances, we can use a sharding approach for the big data. Now, what is different in Hadoop? First of all, in Hadoop, it's usually there's no indexes. Every scan, every Hive query will be a full table scan, and this is important to understand. But on the other hand, this will be in parallel. In Hadoop and in Hive, we have a partitioning, and partitioning is a great way to improve the performance of our queries. And then finally, we have a high level of parallelism. So we have a MapReduce on top of the distributed file system. So let's say we will need to store more data, or we need to process more data and process data faster. We can add a node, so it scales. It scales horizontally. Now let's again talk about the Hadoop differences. There is no indexes. That's a very important point, and all processing is usually a full table scan. But it's distributed in parallel. There's no transactions, and there's usually high latency, because if we talk about Hive, then it will have to generate a MapReduce job. But on the other hand, and someone will ask, how come we don't have indexes? It will be slow. But on the other hand, if we will think about that, how do we create an index for petabytes of data? How we maintain this index for petabyte of data? It will be very slow. If we'll need to add a big chunk of data, it will basically needs to update and sometimes rebalance our B-tree index. How do we read the terabyte index? Even a terabyte index read may be slow. We don't have enough memory for that. How do we perform a random read on petabytes? So let's say we actually solve all those problems and we are able to read a terabyte of index, but then we will end up with lots of random reads of a petabyte data that will be slow by itself. So for the big data, the full scan in parallel is usually better. And this is quite different from MySQL. Now, how do we load our data? In MySQL, we usually have what is called ETL process. Extract data from external source, then transform the data before loading, and then finally load data into MySQL. In Hadoop, it's usually called ELT process. The difference here is that we extract data from external source the same way we do it usually for MySQL, but then we immediately load data into Hadoop as is. So let's say we have a text file. We load this text file into Hadoop. And the reason for that is that we want to take advantage of the parallel processing. When we load the data into Hadoop, that will not be necessarily multi-threaded. That will not take care of parallel advantages of the Hadoop. But then when we will do a transformation and analysis of our data, it will be done on all nodes at the same time. So we will take care, Hadoop will take care of the parallelism in this case. And this is called ELT process for Hadoop. So now let me show you a number of examples of how we load data. First of all, let's say we have a website, online transaction processing with MySQL. And we want to use data analysis with Hadoop and use BI queries. So what we do is we use a tool called Sqoop, which will actually implement our ELT process. So it will extract data from MySQL, and I will show you how we can do that later on. And then it will load into Hadoop cluster, and then on top of that, it will use Hive to execute SQL and run our analysis. Another example, it's a good example of using MySQL together with Hadoop, is to do archiving. So obviously, the less data we have in MySQL, the faster our queries will be. Both inserts and selects are usually faster when the data is small. So let's say our goal is to keep only 100 gigs of data in MySQL. And on the other hand, we don't want to remove this data completely because it's sometimes needed for our data analysis. So in this case, what we can do is to utilize Hadoop for storage and for archiving. And also those data will be available for data analysis. So we will also use Sqoop in this case. We can use Sqoop to extract the data constantly into the Hadoop cluster. We can do a job that will run, let's say, every day or maybe every week, that will extract data from MySQL, delete it from MySQL, and load into Hadoop cluster at the same time. Another example is the clickstream logs or web server logs. We can grab a file from the Hadoop cluster, load it into the Hadoop, and analyze those files with Hive. That's usually what Yoho was doing with Hadoop. And then finally, when we are done our analysis with Hive, we can extract those data into MySQL. So we done our analysis with Hive and we have a report on top of that. And we want to visualize this report. We want to show the picture on top of those analyzed data. So it is easier to do with MySQL. So we export those data back into MySQL, well, into another instance of MySQL and use some standard tools to visualize this data. So I talked about this tool called Sqoop. This is Apache Sqoop, and it's used to import and export data between Hadoop and MySQL. Now let's see how we can actually implement that, how we can play with Hadoop and MySQL together. I will talk and show you about the different integration examples. And the first example is to basically export data from Hadoop to MySQL. And here's how we can do that with the Sqoop. We can use the Sqoop export command to connect to MySQL and get the data from MySQL and load it into the Hadoop. And on top of that, we can always use Hive or Cloudera Impala to analyze those data. And then when I say export and import, I'm talking from the Hadoop perspective. I'm looking at this picture from the Hadoop perspective because I'm using Sqoop, Apache Sqoop, which is a part of the Hadoop infrastructure. So in this example, what we do is we specify the export keyword, we specify the connection string to MySQL, we specify a table orders. This is the table name in MySQL, and we also specify from where we want to get our data. our text files. And here we specify export till results. So we expect that the results will be stored into this directory. And this is directory on top of HDFS. So here we export our results of our analysis, for example, into MySQL server. Here's another example. Let's say we want to take the data directly from Hive. And the user's Hive warehouse is where Hive actually stores our data. And we have this orders.db directory. This is our table, and we take the data from there, and then we specify import fields terminated by. This is the standard delimiter control A that Hive uses. So this is how we can actually export data from Hive directly to MySQL table orders. The next example is import. We import data from MySQL to Hadoop. Same thing, we use Sqoop, we use the import keyword, we specify the connection string, we specify the MySQL table orders, and we can also specify the Hive import. So the data will be loaded into the Hive directly. We can also specify a Hive table so it will know which table it will import into. So this is the way of loading data from MySQL into Hive. Another example is, another possibility is to actually use the Hadoop Applier. Hadoop Applier is a way of connecting our Hadoop cluster to our MySQL replication chain. Hadoop Applier is an alpha software that is actually actively developed by Oracle at this time, and it actually reads the bin log from the master. It's connected to the master, read the bin logs, process it, and we actually need to write a code to implement our processing mechanism, and then we load it into Hadoop cluster, and we can also load it into Hive, obviously. So if you want to try that Hadoop Applier, we can download it from labs.mysql.com. And there's right now there are quite a number of documentation there that you can look at, and it is alpha version right now. And also, it's not out-of-the-box solution right now. We will need to write some code and implement our own logic, how we will process this data. So it will receive the binary logs, we will write the code, it will execute the code that we wrote to process this data, and it will load it into Hadoop. So it's basically a framework, and it only supports the inserts right now. Because obviously handling updates and deletes is hard, because Hadoop only supports the append only. Now let's see and let's talk about the star schema benchmark that I have recently performed. And this is the variation of TPCH benchmark with a star schema database design. And you can look at this Percona website wiki to look into this star schema benchmark in more details. So we will use, for this benchmark, we will use Cloudera Impala because it's a faster SQL. And we will load the data into, I will show you how I loaded the data into Cloudera Impala and how we execute the queries. And this is also a good example of how we can implement the big data analysis. So Impala also supports the columnar storage, and it uses this Parquet storage, columnar storage format for Hadoop. It's a column-oriented storage. It also supports compression. Also, compression is actually very widely used with Hadoop and with Hive. You can also enable compression for Hive as well. Now, as an example of this column-oriented storage, what we did for the Sstart schema benchmark is we generated the raw data, and this is about 1 terabyte of raw data. And when we load it into the Parquet format, it ended up with 240 gigs only. So it's pretty efficient. Now, the first thing I will do is usually what we do with Hadoop is to load all the data. So, as I said, I've generated this terabyte of data and stored in data SSB line order directory inside of my local machine, actually on Amazon EC2. And then I will load this data into SSB line order on top of the HDFS. And I use this HDFS DFS put command to load the data. Now the next thing that I will do is I will create an external table line order text. This external table will be specifying all the fields that we need and also specify the row format delimiter and terminator, fields terminator, and lines terminated by column, and also stored by as a text file and the location. So we create a meta information in Hive or Impala, it doesn't matter, on top of this SSB line order. And we can actually store multiple files inside of this SSB line order directory. It will be easily concatenated by Hadoop and by Impala. And then I would like to actually convert it to the Parquet storage. So I create a new table, line order, like line order text. So I don't have to redeclare all those fields. And then I specify stored as Parquet file. So when I have created this table, I can use insert into the line order, select star from the line order text. So, and this is inside of the Impala shell. So Impala will take care of the conversion. Very similar to what we have in MySQL. And now here are the example queries that we have. We can, this is the query number 1. This selects the sum of the extended price and multiplied by discount as revenue from line order. It actually joins the dates dimension and specify the filter on the date. Another example actually joins 4 tables. It joins the customer line order, the supplier, and dates, and also there are multiple filters on multiple tables. And it groups by and order by. And this is pretty expensive query in MySQL. In MySQL, as we can see, it will have to create a temporary table, will have to do a file sort operation. Right, so this is pretty expensive query. There are a number of other queries similar to this that is part of the Sstart schema benchmark. Another thing, another trick that we can do, both with Impala and Hive, is to do a partitioning. So because many of those queries are actually filtered by year, we can do partition by year. And this is similar to MySQL partitioning. But what it will do is that when we specify partition by year, it will create a virtual field on the year. So after we did that and load the data into this partitioned table, we can actually filter out by the year. Although it's not declared as a part of the normal table, it will be virtual column. And Impala and Hive will be able to take advantage of that and will only read, in this example, will only read 2013 partition. So it will perform significantly less disk IOs. And actually, in this example, what that means is if we partition by year, we have a virtual column on year, we can actually avoid joining to the dates table. But I didn't do that for this example. So here's the Impala benchmark that I did. I used the Hadoop on Amazon EC2. I used 10 M1X large data nodes. The raw data, the text file that was generated by the star schema benchmark generated was about 1 terabyte, 990 gig. The Parquet data was ended up with only 240 gig. And here's the results. So as you see, it is able to scan 1 terabyte of raw data in 50 to 200 seconds, which is pretty good. It's using 10 X large nodes on Amazon. And then there's for some queries, there is quite a difference between the partitioned and unpartitioned data. And again, I didn't remove the tables from the join. So this advantage comes from the partitioning pruning that is implemented by Impala. So what that means is that it knows that it will need to scan only this partition, so it will scan it. And again, unlike MySQL, it's a full table scan. There is no indexes, so it will be able to scan only this partition. It will make a big difference. And then I also did the same example with Hive. And as we see, the Hive showed significantly slower, and the Hive was on top of the raw fields. Also, no, actually, in this example, we use the RC file for Hive, which is also a Columnar storage database. But what we see is that Hive showed significantly slower performance, significantly slower response time than Impala and Parquet. Now, another thing that Hadoop supports is it supports the Amazon EC2. It supports also Amazon has the so-called elastic MapReduce. So Hive can be used with Amazon S3, which is a pretty good feature. So what we can do is we can actually load the data into S3 and create external table in Hive to define the fields. In this example, I create the same line. I create the line item table using the create external table clause, and I specify the, again, row format delimited, fields terminated by, and then the difference is that I specify location, and this location is actually on top of the S3 data. So now Amazon also provides you with the elastic MapReduce. So we can store data on S3. We can prepare an SQL file. For example, create external table, select, and then we can execute the elastic MapReduce. It will start the number of boxes that we specify, run our MapReduce job, and then stop them. And then the results will be loaded to S3 as well. So we can, if we need to analyze lots of data and those data are already loaded into S3, we can easily do that with this feature. Unfortunately, Impala doesn't support that. Impala doesn't support S3 because Impala is not based on the MapReduce. But if we have a data on S3, we can use Hive to analyze that. And that's actually all what I wanted to talk about today. So I will be happy to answer the questions right now. And I will pass that back to Alisa.
Hi, Alex. Okay, let me go ahead and start reading the questions for you. The first question is about the Hive example slide that you used. It says, in your Hive example slide, you are using double floating point numbers for financial amounts. is that a no-no? Typically, you will get rounding errors and should only use floating point numbers for calculating finance charges. Can you comment on this?
Yes, actually, this is true. I didn't actually did an exact calculation in this star schema benchmark. We will probably need to be more precise with what kind of data we will work on. So that's true. We can probably, it's much better to use the precise data in this case, so the calculation will be more realistic. Yeah, go ahead.
Okay. The next question is, in a typical clickstream case, what's a standard number of nodes that Hadoop would run on? Tens, hundreds, thousands?
Well, that of course depends upon the size of this analysis. So if we have, it depends upon the amount of data that we need to process. Let's say we can say that a typical node can be from storing from a couple of terabytes to maybe tens of terabytes of data, and then we can scale it over to multiple nodes. So we can easily, if we need to store petabytes of data, we can easily go with 100 of nodes. There is one with a Hadoop, though. There is so-called the name node, and I didn't get into the details in this presentation, but the name node actually stores the meta information and basically stores the information of where our data is located physically on each node. And the name node is actually a bottleneck here because the name node should store this meta information in memory. So we are limited more with name node rather than the number of nodes. So the typical example, well, it all depends upon the size of our clickstream.
Okay.
Hope that answers the question.
Thank you. The next question is, does Hadoop bring new analysis tools above and beyond MySQL, or does it just make our analysis faster?
It will probably make our analysis faster, and also there are lots of tools that are specific data analysis tools that are integrated with Hadoop. So, for example, like a statistical tools like R, for example, we can integrate that with Hadoop. Another example is we can use the machine learning with Hadoop, and there is a tool called Apache Hadoop that we can use with that. So there are quite a number of tools that we can use for the data analysis, and it also makes it faster because it scales better.
Okay. The next question is, does S3 still have a 5G file size limit?
That's okay. That's a good question. My understanding is that S3N doesn't have this limit, but because Hadoop actually joins the files, and when we create a table in Hive, for example, we actually specify a directory. That may not be a big problem, but as far as I remember, that that's not an issue anymore with the S3N.
Okay.
New version.
Thank you. What do you recommend for tables that have updates?
That's a very good question, and the problem again with that in HDFS we don't have an update capability. So usually usually what people do with this scenario is that they if they nest a number of updates. They not necessarily update the file every time there's a new update in MySQL, for example. So they record those updates and execute it as a batch. And then on top of that, we can use a partitioning, so we will have to actually recreate the file, but we only recreate this small file. We will drop this partition and create a new partition implementing all our updates in a batch. That's a common scenario.
Okay. The next question is, what approach would I use to process user clickstream data in real time?
Oh, this is a common scenario when we use, if we have a file, then we can use Flume. And the Flume provides us with the capability of grabbing a file or reading the file constantly, or we can actually read a socket or anything like that. So we can process the clickstream pretty fast.
Okay, Alex, that seems to be the end of the questions. The only other questions are related to getting a copy of this recording and the slides. And everybody, yes, I will be sending out a link to both the recording and the slides sometime later this afternoon or early tomorrow morning, U.S. Central Time, where I'm located. So with that said, I would like to thank everybody for attending. And Alex, thank you so much for doing today's presentation. Next week is running MySQL on Linux, presented by Peter Zaitsev, who's our CEO and founder. So thank you again, everybody, and I hope that you have a wonderful day, afternoon, evening, morning, depending on where you're coming in from. And again, Alex, thank you so much for today's show.
Thank you, Alyssa. Thank you, everyone.